All right, let's get started where we left off. Who's Walter? Huh? Okay, so I didn't put together. What happened? Yeah, I didn't put together a recap, but I can ask a couple of questions before we get going. Do not look at your notes. Let's see what you remember from lab and lecture last on Wednesday. So, what's the difference between goldfish and soxhlet? The main difference. Okay, Zach? Exactly. So goldfish is a continuous solvent extraction. Soxhlet is a semi-continuous. There is a soaking step. With that, what's the main advantage of soxhlet over goldfish? Or what's the disadvantage of goldfish over soxhlet? Being a continuous solvent extraction, yes, channeling effect. Yes, so with goldfish, because the solvent evaporates, goes up to the condenser and condenses down onto the sample and back to the solvent container. Sometimes it goes through that cycle without taking any fat with it. So therefore, we call that channeling. So it's less efficient than soxhlet that way. All right, good. So both are gravimetric methods. And if let's say we have cheese and we dried the cheese before soxhlet, then we're going to obtain the fat content on dry basis. We can get the fat content by two ways. One way is weighing the flask where we have the solvent before adding solvent in it, and then weighing it after the fat is collected and the solvent is evaporated. Then we get the weight of the fat. Or like you did in the lab, you take the weight of the thimble and the sample, and the difference in weight after fat extraction is the fat that was removed by the solvent. So, and then you get the amount of fat, and you divide it by the weight of the sample, and then you multiply by 100. Okay. If percent fat, now get out a piece of paper for a +2, write your name on it. If you don't have a piece of paper, just give her a piece of paper. Wait, hold on. It's not time to converse. It's time to solve the problem. Okay, so you have percent fat on dry basis is 15%. What would be the percent fat on wet basis if you know the moisture content to be 20%? So this is an exercise. You'll be doing that for the data that we just sent you today. So give it a go. 15% means 15 grams per 100 grams dry matter. So you want to calculate the percent fat on wet basis. That means dry matter plus moisture. Did you get an answer?
Maybe.
What did you get?
12%.
Yeah, that maybe is correct. So, good. So let's see. How did we come up with this? So I said 15 grams fat in 100 grams dry matter or dry solids. Okay? So this gives you the amount of fat per gram of dry solid. But you want it in 80 grams of dry solids because you have 20% moisture. So that would be times 100 minus 20, which is equal to 80 grams of dry matter. Okay, because that's the moisture, that's the total 100 grams of a wet sample. Okay, then with that, you get a percentage of 12%. All right, so all we think about it is that you've gotten the amount of fat in dry matter, so 50 grams and 100 grams of dry matter, dry substance. How much would it be in the actual dry matter in a 100 gram sample? A 100 gram sample has 20 grams moisture, so we subtract the moisture content, you get 80 grams of your dry matter. And this way you get your 12%. And always remember, your dry matter percent or dry basis percent is always greater than wet basis. Then you'll know you did it right. Because sometimes you do the opposite. By mistake, you flip those. And then you get a value that is higher than the dry matter. Then you know that you did something wrong. Go back and look at it to see if it makes sense. Any questions on that? So this is what you will be doing for your lab report. So the fat content for cheeses will be on dry matter, so you will have to do that conversion. The fat content using Soxhlet for other samples were not dried ahead of time. So you would get on wet basis and then convert to dry basis. All right, so the next method for determining fat, which you did in the lab, is the Mouginer method, or Mouginier because it's a French name. So it is a discontinuous solvent extraction. So that means it's a batch extraction. It's not like the solvent is evaporating and then condensing into the sample and the cycle is repeated. No, it is a batch extraction and hence discontinuous solvent extraction. So in this case, depending on the sample you have, for cheeses, you've used ammonium hydroxide. And we did that mixing the ammonium hydroxide with your cheese samples overnight. So what was the use or the purpose of ammonium hydroxide? Does anybody remember from explanation in the lab? Why did we use ammonium hydroxide for the cheese samples, not for the other samples? Yes, Thea? It has to do with the dairy protein. We do not digest it, we solubilize it. So ammonium hydroxide solubilizes the protein because in cheese, your protein has aggregated, gave you a coagulum, and it entrapped fat with it. So you really need to solubilize that coagulum, not necessarily hydrolyze it. So the ammonium hydroxide is actually solubilizing, breaking that network so that you can release the fat. The other sample.
Can you explain how it does that? Because I don't quite understand. Is it so you have the base from the ammonium hydroxide?
So the charges from the base will interact with the charges on the protein and prevent the protein from interacting via hydrophobic interactions. So it kind of breaks the hydrophobic interactions that breaking the bonds between the polymers of the protein. Yeah. Okay, so in the other types of samples, you didn't use ammonium hydroxide, you used HCl, and HCl in this case digested your high carbohydrate and even proteins that were there in your sample. So basically, again, your fat is intertwined with a complex matrix. You have carbohydrate and also protein, and the fat is entrapped with it. So the solvent needs access to the fat. To get that access, we break down the carbohydrate and proteins into smaller units or subunits. Then the fat is free to be extracted by the solvent. You also added 95% ethanol. Can you remember what was the role of ethanol? You know this? Yeah? Thank you. Stop it from clumping. So the ethanol, the alcohol, prevents clumping of your constituents together. So if clumping occurs, fat will be entrapped, and then it won't be extracted efficiently. So the ethanol is added so that the particulates of your sample do not clump together, preventing the solvent. And then we use the combination of ethyl ether and petroleum ether, again to benefit from the advantages of each and counter the disadvantage of each. So to enhance the solubilization of different types of fat in your sample, petroleum ether is cheaper, less hygroscopic than diethyl ether. So you benefit from the advantages of each. So you did 25, I believe, milliliter of one and 25 milliliter of the other. And then you did your vortexing, shaking to extract the fat in the solvent layer. And then you centrifuged and you separated both layers. You actually decanted the solvent into a pre-weighed dish, and then you evaporated that solvent, and you got the fat in your dish, and then you subtracted the weight of the dish, and you got the percent fat that way. For vagina, we didn't have to dry your high moisture foods like the cheeses. There were no need to dry that. The reason that in Soxhlet we dry and here we don't dry is very, very simple. In Soxhlet there is no shaking, no stirring, so there is no kind of enticing of that solvent to penetrate and get into your fat without having to be hindered by the moisture content. So in Mojiner, you vortex, you mix, you kind of force that solvent to get to your fat. Whereas in Soxhlet, no, there's that moisture content that when the solvent is going through, it's just going to hinder it from reaching the fat and taking it with. So in this case, that's an advantage for Mojiner, is that you can analyze as is without having to dry your sample. So again, as a reminder for you as you calculate your concentration of fat, all cheeses using Mojiner were not dried. So you get fat content for Mojiner on a wet basis. Okay, so remember that when you're doing the calculation. All right. Now I'm going to briefly talk about two other methods for extracting the fat. And you are not going to use those in lab, but they are very common. One is the supercritical fluid extraction, where you use CO2, and then under certain pressure and temperature, the CO2 becomes liquid, and it's pumped into the cell where you have your sample. So the liquid CO2 acts as a really good solvent for hydrophobic lipids. And sometimes you add methanol to can also extract the more relatively polar lipids. So you have a combination of your methanol and CO2, or if you use just CO2, it would be fine. It would mostly extract your triglycerides. And then from there, after the solvent extracts, the solvent passes through tubing and then gets collected in a collection vessel or vial. And because the pressure is lower to atmospheric pressure, CO2 becomes gas again and leaves the system, and you end up with your fat. So it's pretty straightforward and simple. And this kind of extraction is sometimes followed not just for fat, for other components as well, volatiles that are hydrophobic, so they can be extracted that way and linked to the GC directly because of the simplicity of it being in CO2 matrix. The other one is the elevated pressure temperature or accelerated solvent extraction. Here, instead of having CO2, you have your regular solvent. But if you use your regular solvent under pressure, then your boiling temperature increases. Therefore, you can have more efficient extraction with your solvent at higher temperature. So you can increase the temperature and have better efficiency of extraction before the solvent is evaporated. So basically, you're increasing the boiling point of your solvent under pressure. And you can run this as static. That means you do your extraction with the solvent, and then you open the valve, the solvent goes into your collection vial. Or you can have it continuous, like a continuous success or semi-continuous success extraction, where the solvent, this valve is always open and the solvent is continuously going through the chamber where you have your sample and continuously getting your fat. That would be more expensive because you would need to use more solvent, obviously, than the static mode where you let it soak and then get the solvent and separate the solvent from the fat. You can do a combination of like semi-continuous extraction of static, where you have a soaking step, and then you open the valve and allow fresh solvent to go in and extract again and collect more. That will give you more accurate extraction or more complete extraction of your fat. And that is kind of an automated system of an accelerated solvent extraction. And here you can do extractions of not just fat, any other organic matter that is soluble in organic solvents. Okay, so the last form or forms of fat determination, it is the non-solvent extraction and wet extraction method. And this backcut is the most common one for dairy products. So you have one for one flask for milk, for cream, and for cheese. If you notice the cheese, instead of pouring the milk and the cream inside, there is a stopcock that you take that out and then put your cheese sample in and then close it. So it is very simple and quick. It takes probably 40 minutes or so to run the analysis. So you would put a certain amount of your, here in this case, milk, and I believe it's like 17.6 milliliter. And then you would add similar volume of H2SO4, a concentrated acid, again about 17.6 milliliter. And then what happens is the concentrated H2SO4 is going to digest the sample and generate heat. So the sample is being digested, so your protein and carbohydrates are being digested, and they would remain in the aqueous compartment. And then your fat, because of the heat, will be solubilized, and then it would rise to that graduated neck here. Because fat has lower density than your aqueous, so it will be on top. And then you will just measure the amount of fat on top here. And the reason we have a specific amount of milk and specific amount of H2SO4 is to drive your fat layer to the place where you can actually take the measurements for the volume. And again, here you don't need to dry the sample, and it is a volumetric means of measuring. So you measure the volume of fat in a certain volume of milk, So then you can convert that to grams per 100 grams, and I'll show you an example. And the procedure would be the same for cream or cheese. It can be used for other types of products too, but it can be used. It cannot be used with samples that are high in sugar, because the fact that the sugar gets burns and cause charring. I mean, so it will be black and then it will be hard to read. So you cannot use it with high sugar, chocolate with high sugar, for example, or added sugar. The Gerber method is kind of a similar method to the Babcock, and again, Gerber is the name of the person, the scientist that developed it, and Babcock is the name of the scientist. I think Babcock was from Wisconsin. There is a Babcock Hall in Wisconsin. Okay. So anyway, this is very similar method, smaller tubes. You also use H2SO. The main difference is that with the sulfuric acid you use amyl alcohol, and this prevents the charring of sugars. So you can use it with products that have added sugars in them, like milk chocolate, for example. So you can do that. So same principle. Not going to spend more time on that. Okay, so both Babcock and Gerber are volumetric methods, not gravimetric, so it's not based on measuring the weight. But here's an example. If the milk fat density is 0.9 and milk density is 1.0332, and you got a percentage of fat on a volume basis in milk to be 3.55 milliliter per 100 ml. So it is volumetric, so volume per volume, 3.5 milliliter per 100 milliliter of milk. What would be the percentage of fat on wet weight basis? That means grams per 100 grams. So what would be grams of fat per 100 grams of milk? So think about it, use it on that same piece of paper to be turned in. Okay, anybody? Rita?
I got 3.096.
3.0? Yeah, 3.1 for simplicity, yes. So the way you do that is you convert volume to mass or to weight using the density. Density is mass per volume. So you have the density for the fat is 0.9 grams per milliliter. Where did I Okay, so 0.9 grams per milliliter is your density for fat. And then density equals mass over volume. So mass equals density times volume. So basically the mass of fat is the density 0.9 grams per milliliter times the volume, which is 3.55 milliliters. And this will give you 3.195 grams. So now I have the grams of fat in 100 milliliters of milk. So I need to convert 100 milliliters of milk to a weight. So the density of milk is 1.032 grams per milliliter. So then my mass or weight for milk equals the density 1.032 grams per milliliter times 100 milliliter. Then I get 103.2 grams. So now the percentage, that would be this in this times 100. So 3.195 grams in 103.2 grams. Times 100 for a percentage, then you get 3.1%. Okay. So lastly is instrument-based methods. So we've talked about IR, where you can use near IR or mid-IR. Mid-IR is mostly used with dairy or milk samples. Near IR can be used for different sorts of samples, and it's based on absorption of IR energy by the different functional groups of the fat. So it does require calibration with official methods of analysis or wet chemistry-based methods of analysis, and it's fast. It can be online and for quality control methods. The Fosler method, you no longer will find it in your textbook. It was removed, but I still like to put it in there because it's a traditional method that is based on measuring the specific gravity of a sample solvent extract. That means you extracted your fat from a sample using perchloroethylene type of solvent, and then you measure the specific gravity of that extract, and you can convert it to percent fat using a conversion chart that relates the specific gravity to the amount of fat in your extract. Lastly is NMR. While the principle is complex and analyzing the spectra is not very intuitive, but it's very easy and gives you good accurate measurements for the amount of fat. That's it for fat analysis. Should I send you home? No. No, we have 20 minutes. How much do you hate me, Paige? 20 more minutes. What's better than ending your day with a carbohydrate lecture?
Eating carbohydrates. Taking that out. You got quality after that.
Oh, you got quality. Okay. But then this will help you drive you, gives you energy, carbohydrate, energy, so that you can be very attentive to Tonya in her lecture. Okay, carbohydrate analysis. Last bit of measuring different large constituents in food. Let's see, food chemistry check. Which of the following is a carbohydrate? Have you had the carbohydrate in the food chemistry yet? I'm going to go with Dan and Adele.
All of the above.
Dan goes with all the above. Same? Fired. No, I'm just kidding. Who else has a different answer? Cece. D. Thank you. Lignin is not a carbohydrate. Lignin is a dietary fiber. Cellulose, pectin are dietary fiber as well, but they are carbohydrates. Now, what differentiates a compound from being called a carbohydrate versus a non-carbohydrate? What's that?
Carbon and hydrogen.
Well, there is carbon and hydrogen also in lignin. There are polymers, right? So the subunits differentiate whether it's a carbohydrate or not carbohydrate. The subunits, are they sugars or non-sugars? So if you look at the lignin, that says lignin, it's a large polymer, but can you see in this polymer any sugar subunits? Wow, no, there is no sugar. These are benzene rings and some OH. There is carbon, there is hydrogen, but there is no sugar as subunits. So these are the subunits of your lignin. Okay, so they are non-sugar, they're alcohol, and there's benzene ring there. So, but what makes them all dietary fiber? What makes them all part of a dietary fiber? What's the definition of a dietary fiber? You guys know this, just be brave. Go. Indigestible, large molecules that our body does not digest, does not have the enzymes needed to digest these large polymers. So we call them dietary fibers. That's simply the definition. Non-digestible components. The definition doesn't say carbohydrates. The method used to determine starch gelatinization could be used to determine starch retrogradation. Should you know this? No, you shouldn't know this. I will explain it later. But the point I have this up here is I want to know if you know the difference between starch gelatinization and starch retrogradation. Yes, Sammy? You want to say it's true? It is true, but I will explain that later. But do you know the difference? Not just Sammy, anybody. Do you know the difference between, what is starch gelatinization? You should all know this. All of you. Huh? Brigida.
Starch gelatinization is it when the starch is heated up and then it becomes swollen because the water gets into the starch. And then retrogradation is when you store the starch in the fridge and then the hydrogen bonds link back together.
Okay. Yes, but you don't have, it doesn't have to be in the fridge.
Okay.
Okay, so starch gelatinization is when you apply heat and the presence of moisture, your starch granules swell. So, and then they become viscous. They can form a gel. Okay, and they are digestible. The starch that is gelatinized is digestible. Raw starch is not as digestible, or very limited digested, very slowly digested. Whereas retrogradation, over time, your starch molecules, amylose and amylopectin, recrystallize. That means they bond with each other via hydrogen bonding, yes, and they form crystalline structures. So that's how your bread stale over time. Okay? This is how your pasta is formed, due to crystallization of amylose mainly, and the retrogradation in bread is mostly due to the slow retrogradation of amylopectin. So amylopectin retrogradates slowly, whereas amylose retrogradates fast. Okay, that's why in pasta, high amylose to amylopectin ratio would be desirable to produce your pasta. Okay. Importance of carbohydrates. Page. Energy. See, that's why this lecture is important. Source of energy. Great. What else? Page. I thought you were tired. Go ahead.
Fiber.
Source of fiber. Do I have it in my notes already? Okay. Yes. So carbohydrates can be, the non-digestible carbohydrates are part of the dietary fiber. What else? What's the role of carbohydrates in terms of functionality in foods? You work in George's lab. Texture, yes. Building texture, viscosity, gel, stability of emulsions. When you have a viscous continuous phase, your emulsion is more stable than a less viscous emulsion, less viscous continuous phase in an emulsion. People think that the proteins in bread are the most important components. They are very important, but the starch is very important too, because when you bake, you are building the structure of the starch that will also stabilize the foam or the cells in the bread. So it's not only gluten, it's also starch. So it's definitely for functionality and texture. More. Tell me more. Okay. Yes, thank you very much. Building flavor and color, not just flavor. Color, browning from the Maillard reaction, or caramelization from burning the sugar, producing your caramel. Yes? Fermentation, yes. Fermentation, we need the sugar, we need to ferment. The yeast need to eat to give us a fermented product. Yes, I don't have it on my slide, but yes. Clean.
I feel like we needed to calculate something on the nutrition label.
We need the sugar. That is for why do we analyze? That's coming up later. But there are a couple more that is very important. What happens to your water activity when you have high sugar content? It goes down. So sometimes, sugars are preservatives. So fruit preserves, jams. So in the olden days, how do you preserve fruit? You add sugar to it, and then it lasts longer. And one last thing I have here. Yes. What's that?
You can prevent like moisture transfer.
Yes. Yes. You can hold on to the moisture and prevent moisture transfer. Yes. Okay. I have one more on the slide here that I don't know if you're gonna. Anybody might guess? A trendy thing, resistant starch. So resistant starch and glycemic index. What is resistant starch? I'm going to tell George on you, each one of you. I'm going to give him the list of names and say, -2 in your class, George. What?
Resistant starch is one that's more slowly digested, so whether it's more cross-linked or bound to other things.
Okay. Yes, resistant starch, from its name, it resists digestion. Very, very slowly digested, and there are different levels of the speed of digestion for the resistant starch. There are 4 different types of resistant starch. Resistant starch 1, 2, 3, and 4. No clue. You didn't tell me honestly. Did you cover it in food chem or not? You did. Honest. You are honest. I appreciate that. +1 for everybody for being honest. Okay, so resistant starch. Retrogradated starch is a resistant starch. Raw starch is a resistant starch. Chemically modified starch is a resistant starch. Starch that is bound within a food matrix and is not accessible by enzymes is a resistant starch. So there are your 4 types of resistant starches. I'm going to ask about this in the exam. Okay. Why did I reveal that? Yes, Adele. Great. Thank you. You still get your +2. Never mind. Here you go. Okay. So here we go. Quality control, ingredient authentication, and for labeling. And for labeling, it's not like we analyze carbohydrate. We determine it by difference, but there are 2 components that has to be there, the dietary fiber and total sugar. So these are individually analyzed. So you get the total carbohydrate by difference, but then there are certain components that you need to analyze so that you can put them on the label. Research, definitely carbohydrate. People continuously look at sources of fibers, the differences in fiber. You have your hand up? No. The difference in the fiber components, looking at the functionality of the different components, of whether it's starch or whether it is modified starch or dietary fiber. There's always research involved there. Product development. Uses of different starches that have different characteristics, whether it's chain length or amylose to amylopectin ratio or different dextrose equivalent. Why would we need to use them, and how would they produce different functionality in food products? Okay. Carbohydrate classification, just a simple reminder. We have the monosaccharides, and we have the disaccharides, trisaccharides, and oligosaccharides. They go from 2 to 10 units. Okay? And then you have your starch that are polymers of glucose units, and some are like the amylose is less chain than amylopectin, and then you have the dietary fiber that have different subunits. We'll talk about that later. So these are your polysaccharides. Remember, I say dietary fiber here with the exception of lignin. Okay. We have 5 minutes, but since I'm going to go into analysis and preparation, it's a good stop. So I'll stop here. 5 minutes extra, see?